What's going on, everybody, and welcome back to the Aimtec Academy. The best spot to learn more about how Aimtec power converters can be used within the power supply industry, as well as increase your overall general knowledge about this market. So the topic for today's course is going to be about EMC. So how to actually use Aimtec's EMC filters, how Aimtec EMC filter product lineup could actually help you guys meet specific EMC standards, as well as a brief look at certain customer applications where using our filters actually help them achieve the EMC standard that they wanted to meet. Without further ado, let's hop into the course. Welcome to Aimtec's course on EMC. So today what we're going to be talking about is what EMC is in general, the different EMC standards, what EMC filters are, as well as the type of different EMC filters that Aimtec offers. And then we'll finish the presentation with EMC Filter Applications. So what is EMC? EMC is composed of two things, so EMI and EMS. EMC stands for electromagnetic compatibility, EMI stands for electromagnetic interference, and EMS is electromagnetic susceptibility. Now, what we mean by susceptibility is how much the device under test, or DUT, is affected by the world around it. Or in other words, the highly susceptible device is prone to be affected by electromagnetic interference coming from other sources. So if you have a highly susceptible device, then EMC or EMI, or the interference created, is going to be much more impactful than a device with low susceptibility. So now EMI is actually composed of two different types of interference. So you have the interference that comes from conduction and the interference that comes from radiation. So on the left we have an anechoic chamber which can either reflect or absorb energy, and this is used for radiated testing. So there's an antenna that is used to receive the radiated EMI generated by the DUT, and this is how they actually measure how much EMI is generated. So on the right side, we have the conduction test, and this is used to measure the conducted EMI generated by the DUT and transmitted through the conduction line. Now we're going to talk about EMS. As we mentioned earlier, it's how much the DUT is affected by the world around it. So these are the various test items of the EMS test standards. So we have the electrostatic discharge immunity. So that's the immunity of the actual component to withstand a sudden electrostatic discharge. The next is the electromagnetic field immunity. So again, there are many magnetic fields in the environment around us, and some of them may actually impact a component. This will tell us how well the component can resist the electromagnetic field. The next one is electrical fast transient burst immunity or surge immunity. So power surges happen all the time. Sometimes they can be very detrimental to the power supply. This will actually tell us, or surge immunity will tell us, how well the power supply can withstand to surges. Conducted disturbance immunity is noise that gets to the component in a conducted fashion. Power frequency magnetic field immunity test is to test how well the DUT can handle the magnetic fields at AC main frequencies. Voltage dips, short interruptions immunity will tell us how the component will perform if voltage dips or short interruptions occur. So now moving on to the different EMC standards. We have two main groups that mandate the EMC standards, which are referred to around the world. We have CISPR 32, which is a current European standard for electromagnetic compatibility set up by the Comité International Spécial des Perturbations Radioélectriques. We then have FCC Part 15B, which is the equivalent American standard set by the Federal Communications Commission. Although both standards are harmonized, there are some minor differences between them that is beyond the scope of this course. Below, we can see two test graphs. These are typical measurements taken on a logarithmic scale showing how the DUT, or device under test, behaves under different frequencies. The red line represents the maximum allowed signal strength, or noise level. The DUT will fail the test if the peak reading goes beyond the red line, or if the average reading goes beyond the green line. The more margin we have, green line or lower, the more confident we are about the effectiveness of the EMC circuit. On the left-hand side, we have the conducted test results, which are plotted on a lower frequency, typically from 0.15 to 30 megahertz. And on the right-hand side, we have the radiated emission test results, which are measured on a much higher frequency, which ranges up to 1000 megahertz. The y-axis shows us the amplitude and is measured in decibels, or decibels per microvolt. This is a screenshot of the AMEOF 15-277NZ datasheet. Under the safety specification standards, we have either our certifications, what our components are designed to meet, as well as the different standards that the component can actually meet. On the first row, we show what standards our components are designed to meet. If we do have a certification for it, it will also be listed on this first row. Right under the first row, we have the different standards that make up EMC. We actually talked about this previously in the course, but on the left-hand side, we have the different categories, and on the right-hand side, we have the different standards that they actually meet. So in this case, if we're looking at the first row after the Design to Meet row, we have EMC, so conducted and radiated emissions. And on the right-hand side, we have the different standards. So for it to meet the EMI Class A circuit, you need to follow the typical application circuit that we list in our datasheet. If you want to meet the Class B circuit, then you need to follow that specific circuit to meet the Class B. For our AZ models to meet Class A and Class B circuits, the only thing that you need to add is a 0.33 microfarad capacitor between the AC line and the AC neutral. So going through this table, you can see which standards that the component actually meets, and if any external circuits are required, then they will be listed here, and then you will be able to find an actual diagram of those circuits further on in the datasheet. So right below, we have two graphs that show us that Class B is actually more stringent than Class A. So just as on the previous slide, the red line is the maximum threshold to actually comply to the standard, and then the blue line is the average. So if we have a peak reading above the red line or an average reading above the blue line, then the component will fail the EMC test. Now we're going to be moving on to the different types of EMC filters that Aimtec offers. So to begin, we're going to look at AC EMC filters and look at how Aimtec actually labels them. So first off, we have AM, like all of our part numbers, which stands for Aimtec, and then the F after the AM is for EMC filters. The E is for an AC, so if it's DC, you will not have an E in the part number. So the next three digits after the E are going to be the maximum input voltage. Next, we're going to be looking at the maximum input current. After the dash, the LN stands for line to neutral. The X means the level of surge suppression. So a 1 would mean plus or minus 1 kilovolt, and a 4 would mean plus or minus 4 kilovolts, where in this case, higher is better. And then the last digit is the factory code. Now this is a typical example of how Aimtec EMC filters can actually be used. So we have our filter on the left-hand side, and then we have the AC-DC converter on the right-hand side. So what you see on the right-hand side in yellow are the standards that come standard with the AC-DC converter, and then once you add the EMC filter, you see the result in red. So when it comes to electrical fast transient immunity, with no filter, we can hit plus or minus 2 kilovolts. When you add the filter, you can go all the way up to plus or minus 4 kilovolts. So you double this electrical fast transient immunity by adding an EMC filter to your design. Same thing when it comes to surge immunity. You can effectively double the amount of immunity that you have to surges by adding an EMC filter to your design. This is a typical application circuit when it comes to incorporating an Aimtec EMC filter into your design. So you will be adding the EMC filter before the actual Aimtec converter, and you also need to integrate a fuse. Now we're going to be looking at DC EMC filters and how we number them. So AMF, as for the AC-DC filter, remains the same. The letter A refers to the input voltage range, so if it is a 2x1 input range, then it will be blank, so there will be no digit there or no character. If it is a wide input voltage range, then there will be a W. The next three letters stand for the nominal input voltage. The following two, if they're left blank, mean that they are an EMC filter. If there is FT, then they are an EFT suppressor. The next three digits after the dash refer to the input current. For active filters, the maximum input current under nominal voltage is what will be described. And for passive filters, we're just looking at the maximum input current. The next letter, if it is an N, refers to active filters, and if it is a J, it refers to a passive filter. And then, just as in the other case, the last character refers to the factory code. So just as for the AC-DC EMC filter, the DC-DC EMC filter needs to be placed in front of the Aimtec converter, which in this case is a DC-DC converter. If we integrate the EMC filter, we can actually bring the EMI performance from Class A to Class B and make the system able to withstand plus or minus 6 kV of contact electrostatic discharge and plus or minus 8 kV of air electrostatic discharge. And again, this is the typical application circuit that you also find in the datasheet. As for the AC EMC filter, you will need to add a fuse. But for the DC EMC filter, you also have to add capacitors. Adding capacitors actually increases the filtration. Finally, we're going to talk about EFT suppressors. So adding Aimtec EFT suppressors can ensure that Aimtec DC-DC converter modules meet the EFT level of plus or minus 4,000 kilovolts. So what happens is that in the left-hand side, you see the graph where you have a burst of excess switching energy, and after adding the EFT suppressor, this large burst gets reduced, and anything above or below the dotted lines gets rejected. So this is a typical application circuit for Aimtec EFT suppressors, which will also be found in the EFT suppressor data sheets. You can either add an EFT suppressor before or after the converter, and sometimes both. It all depends on where you will be expecting to get a surge. So if you expect that there will be a surge in front of the DC-DC converter, then you'll add one before. If you think that some external factor may affect the DC-DC converter, causing it to create a surge, then you can add an EFT suppressor after the DC-DC converter as well in order to suppress it. So depending on the application, you may need 1 or 2 EFT suppressors. If you have any questions regarding this, don't hesitate to contact Aimtec's product team. Now we will be moving on to common mode chokes. So again, it starts with AMF as all the Aimtec EMC filter part numbers. Next, we have the C representing that it is a common mode choke. The next two letters refer to inductance. So the next two letters measure inductance as shown in the table on the right. After the dash, the Y stands for the maximum input current. So if it is 0.3 amps, we're going to have 0.3, and if it's 1.5 amps, we'll have 150. And then the last two letters refer to the factory code. So when using common mode chokes, there's two actual modes that we can see. So we have differential mode noise, which is on the left, and then we have the common mode noise, which is on the right. Now the noise in the diagram on the left is generated because we have current that passes through the wire, and that in and of itself will generate noise. On the right-hand side, we also have the noise generated from the current passing through the wire, but we also have a ground, and this ground can also create additional noise. So in other words, differential mode noise is conducted on the signal line and the ground line in opposite directions of each other. Common mode noise is conducted on all lines in the same direction. With an AC power supply, for example, noise is conducted on both lines in the same direction. With the signal cable, noise is conducted on all the lines in the cable in the same direction. So it's important to understand your circuit in general to see where the different sources of noise will be coming from and where you can actually use these common mode chokes to suppress this noise. So Aimtec offers many different models of this common mode choke, and depending on the different amplitudes or frequencies that you want to attenuate, you'll need to use a different model. So in the graph on the right, you see the attenuation specifications. So your y-axis is the gain and your x-axis is the frequency. So as you can see throughout the graph, you have different model numbers within the common mode choke product series, and those different model numbers will attenuate different frequencies. You can choose the different models by knowing exactly which frequency and gain that you will need to work with. But in order to find the best fit, we recommend that you contact one of our field engineers and they will help you select the proper common mode choke. So now moving on to different EMC filter applications, we're going to start with the cart monitoring system. So as you can see in the block diagram, we actually add a DC EMC filter before our brand new AM50QB-JZ series of DC-DC converter, which are specially designed for railway applications. We add this filter as an extra layer of protection to make sure the system can run error-free when there are surge or strong interferences in the circuit. Since there are lots of vibrations and high voltage sparks on board trains, there are high EMC requirements, which is why we actually added an EMC filter in this application diagram. Next, we're going to be looking at a plug door control system. So again, we have our Aimtec DC EMC filter right before our DC-DC quarter big 50-watt converter. In this case, our customer could not meet the EMC standard without a filter, but after adding our filter, they were actually able to meet. So it's much simpler to add a filter in order to meet the design than to have to redesign the whole circuit to meet it without a filter. So sometimes adding a filter to the circuit is the simplest way to actually meet EMC. So as we can see, the current goes through the DC EMC filter first, and then goes to the 50 watt DC-DC converter, and then supplies power to our 1 watt AM1DR and Z, which then powers the 485 communication and the main control board. Looking below, it also powers the AM6CW-NZ, which powers the LDO. And now this is how a DC EMC filter can be used in the feeder terminal unit, or FTU, of the smart grid. And essentially what this FTU can do is it can report the status of the power line. For example, if the power is down or if there's abnormal power usage. When we're looking at the power grid, there's lots of transients due to lightning strikes, trees hitting poles, transformers blowing, etc. In order to keep the FTU functional during all this time, they need surge suppression. This is why we have different Aimtec surge suppressors in the block diagram. Next is the milk analyzer. So what this milk analyzer does, it identifies how much nutrient is actually in the milk. And in order to get accurate results, you need to make sure that enough filtering is done, because the noise generated by the circuit or external components can actually mess up the readings. So in this case, we're using an AC EMC filter, which then powers the AME25-MJZ AC-DC converter, and this supplies power to the AM6TW-NZ as well as the AM1DM-NZ. Finally, we're going to look at the BMS, or Battery Management System Conductive EMI solution. We don't want noise in the BMS because that can falsify readings, and since the mode is common mode noise, we will be using a common mode choke to suppress it. Once again, as a reminder, you need to select the best common mode choke based on the different frequencies that you want to suppress. You may need 2 chokes if you're dealing with 2 different noise levels. So in this example, we have the first common mode choke and then the second common mode choke, which actually deal with 2 different noise levels. Again, on the datasheet, you can see the graph displaying which common mode choke should be used for which frequency. Finally, the power is supplied to the AM6CW-NZ, which then powers the MCU. Well, that concludes our course on EMC filters. We hope now you have a better understanding of what Aimtec EMC filters can actually do and how they can be used in the field. Again, if you have any questions, don't hesitate to contact us at sales@aimtec.com or support@aimtec.com, depending on the type of question that you may have. Good luck on the quiz, and we will see you in the next one.